finishing up the introduction to dark matter in chapter 28. We're going to talk about, dark matter. How do we know where it isn't? How do we know where it is? What even is it? So, in our solar system, the sun is in the center and is far and away the most massive thing in the solar system. And so things that orbit it close in have a higher orbital velocity than things that orbit around the outer edges. That's because the solar, the center of our solar system is our sun, and we don't find any unexpected measurements in our solar system. When we were studying Uranus early on, we did find unexpected measurements. Oh, and wow, they were caused by Neptune. But we don't really find that anymore, so we don't think that there is dark matter in our solar system. Let's compare that to galaxies. We've already stated that we find dark matter in galaxies, so let's look at the 4 lines of evidence and where we find them. So we looked at a rotation curve for a galaxy already. So for the Andromeda Galaxy, which is a spiral and is rotating, we can observe the movement of stars and, calculate the amount of time that it would take for them to make one orbit. And what we expect, if we are expecting the world to follow Kepler's laws, which we do, and we assume that the mass of stars in the bulge and the supermassive black hole in there are the majority of the mass in the galaxy, then we expect the rotational curve to follow this blue line and, very quickly accelerate to higher velocities and then slow down the farther you get out from the galaxy center. That is not what happens. Instead, we see that, the rotational velocity continues to increase. So there must be mass out in the outer edges of those galaxies to balance the mass in the center. We've already looked at gravitational lensing, but it really is one of the sources of evidence for dark matter. This is galaxy cluster Abell 2218. It's about 2 billion light years away from us, but if we look at this image, we see all the galaxies, the bright shiny yellowish spots, but we also see all of these little wispy lines that more often than not are blue, but a couple of them are red, a couple of them are multicolored. Those are galaxies that are far away and being lensed by Abell 2218. So we take the galaxies in this cluster, estimate their mass, which we can do pretty accurately, and we see that the galaxies behind are lensed way too much to balance the amount of mass that we can see in the galaxy cluster. So, dark matter isn't anything other than matter that you cannot see. Another line of evidence for dark matter is X-ray emitting gas. So, different galaxy cluster, this is Abell 1689, distance of 2.3 billion light years from us, and you see all the galaxies in there, but in between the galaxies we have a huge amount of X-ray that is being emitted by the gas, the interstellar gas between the galaxies. Something is whipping that gas around so that it is moving around the center of that cluster so fast that the gas itself is emitting X-ray. That requires enormous speeds, and the only way to have that much speed is to have an enormous amount of mass there, much more than what we can identify. And then we're going to finish this up by just talking about the fact that dark matter actually gives us the seeds for galaxy formation in the beginning. When we started talking about galaxies, we talked about the structure they have now, but how do they get that structure? And so we sort of have two possible scenarios at the moment. A hydrogen cloud that collapses under gravity. Well, where does that gravity come from? It comes from all of the matter in that cloud, and if there's dark matter in the cloud along with the hydrogen and gases that we can see, then suddenly there's enough matter and mass in that cloud to make it collapse. The other one is that we have, a disk galaxy and a companion, and the companion falls into the disk. And so either way, we end up with these central bulges forming over time, but those are the two best explanations we have for how we get that central bulge. And then, growing galaxies, how do we grow them? Well, we've already talked about galaxy cannibalism and that one galaxy will eat another. This happens for clusters as well. This is, the core of a galaxy cluster far away. This is Sparks 1048 plus 56, which is just a name. But if we look at this image, this really can very easily be described as a train wreck. Everything is running into each other, and there's these streamers and arms of star formation. So we have several galaxies colliding into each other to form, bigger galaxies. And when we start talking about the Big Bang, next chapter, at the Big Bang, the universe was fairly uniform, but small. And then as we continue to expand, just like you stretch spandex fabric and you can stretch it enough to see the holes between the threads, our homogeneous galaxy, you stretch it and those galaxies will collect together and form streams that, stay together with huge voids in between. And then a schematic drawing of, how galaxies might have formed from small clouds of gas that clump together, forming, bigger clouds and bigger, and then end up with galaxies. And our clusters of galaxies pull together. All of this relates back to dark matter. So, thank you very much for listening.